Welcome to the fifth presentation in the sixth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the fifth webinar of our sixth series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the sixth series will be distributed through the IAS mailing list, Twitter feed, and LinkedIn page. Today's webinar will be given by Dr. Marc-Olivier Coppens at University College London in United Kingdom. It is also part of our IAS webinar series titled Diffusion in Nanoporous Materials, Guidelines for Measurement and Reporting, focusing on the recent IUPAC technical report, Diffusion in Nanoporous Materials, with special consideration of the measurement of determining parameters. I am Nicholas Wilkins at Svante Technologies Incorporated in Canada. Today's webinar will be moderated by Bhupesh Murugapan at University of Alberta in Canada. We're required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you're not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @adsots for future updates regarding IAS events, webinars, and information about scientific meetings. We've also started a LinkedIn group, which can be found by searching the International Adsorption Society. Please help us expand our YouTube channel by liking this video and subscribing. We would like to remind the attendees of the 15th Fundamentals of Adsorption Conference that is being held this year in Porto, Portugal between May 18th and 23rd. Additional information can be found at the URL given on the slide. We look forward to seeing everyone there later this year. I'll now hand it over to Bhupesh Murugapan, who will moderate the YouTube Q&A.
It is my pleasure to welcome Dr. Marc-Olivier Coppens to today's webinar session. Dr. Coppens is the Ramsay Memorial Professor of Chemical Engineering at the University College London. He has also held professorships at Rensselaer Polytechnic Institute in the United States and at TU Delft in the Netherlands. Dr. Coppens has also served as the Vice Dean of UCL Engineering and Head of Chemical Engineering Department at UCL. Dr. Coppens holds MSc and PhD degrees in Chemical Engineering from the Ghent University in Belgium. He was also a postdoctoral research fellow at Yale and UC Berkeley. He is recognized for pioneering nature-inspired chemical engineering, that is NICE, to develop systematic nature-inspired solutions to accelerate innovation for sustainable development. He also directs the Center for Nature-Inspired Engineering at UCL. Dr. Coppens has received numerous accolades, including the RSC Catalysis Science and Technology Lecture Award, Young Chemist and Pioneer Awards from the Dutch National Science Foundation, UCL Education Award, among various others. He serves on the advisory boards of multiple journals, including RSC Molecular Systems, Design and Engineering, and is also the editor-in-chief of the Chemical and Engineering Processing, Process Intensification Journal. Dr. Coppens' multidisciplinary research combines fundamental theoretical work with experiments to understand the effect of heterogeneity on transport phenomena and developing multi-scale porous catalyst models, all of them to aid development of sustainable solutions. During the webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I welcome Dr. Marc-Olivier Coppens again and pass over the presentation to them.
Thank you very much, Pubesh, and indeed also Nicholas for inviting me and for this webinar. I'm going to try to share my presentation now. There we go, and I hope you can see this.
Yep, we're able to see it and hear you well.
Yes.
Wonderful. Well, as I'm really excited to share with you some work on diffusion mesoporous materials, which is a very broad topic. I mean, you often hear about diffusion in zeolites and microporous materials, diffusion in materials in general. And here I'd like to focus on these mesoporous materials. And I hope to demonstrate to you that there's a lot of interesting things to be learned about these materials, that there's been progress on the fundamentals, but still a lot of open questions as well. And it's really crucial to see how we can link better the evolving theories to describe diffusion in mesoporous materials with experiments. And so this has become also a part of the IUPAC report I will get back to later in my presentation, and which was mentioned earlier. So there's really a great variety of porous media. I mean, in catalysis, as adsorption, membranes, but also in insulation, food, pharma, building materials, and so forth. And in all of these, transport phenomena are extremely important. And it's important to be able to describe mass transport, in other cases, heat transport as well. But the question then is, how do we relate a porous material model first to experiments? We first need an appropriate model for these porous materia to be able to describe, say, diffusion in such a material. So one way is that it is inferred by the way that these materials are manufactured, synthesized, or emerge. There's, of course, experimental characterization techniques that give us insights into these materials. And then there are reconstruction methods using statistical properties. So I'll briefly say something about these as the foundation for these models for porous media. So first example, which I will get back to also at the end of my talk, is about correlating synthesis to a model for, say, a very common porous material used in industry for adsorption, catalysis, a catalyst support, which is gamma alumina. And so this is something, for example, that IFP Énergie Nouvelle in France have been studying, and we've had some projects together, also in the context of Hurricane network. So in these materials, they are hierarchical materials. You have alumina platelets, you have aggregates formed out of nanoparticle, and you have an intra-aggregate pore space. And then between these aggregates, you also have a pore space. And so the question is often how you then really relate the original nanoparticles with the eventual material. And that's important to be able to predict transport properties, to predict also diffusion and reaction when this material you see here on the right is used as a catalyst or catalyst support all the way for industrial processes. For example, gamma alumina is used as a support for platinum and platinum rhenium in catalytic reforming, used in refineries at enormous scales around the world. So clearly, this is one way. Can we understand and correlate synthesis to models? Now, we have a lot of tools now to look at materials. I mean, there's a very nice review published a couple of years ago by Gabriel Pérez Ramirez and his group, which shows really the breadth of these techniques of imaging them. So this goes from imaging really from the nano and atomistic scales, TM techniques, all the way via particles, pellets, and also how pellets are distributed in the reactor, and even visualizing the flows within these reactors with X-ray techniques or with an NMR. Then there are other techniques, and I mean, these are some images from our own labs about, probing clearly the porosity, and this is something many of you use and work on. Adsorption techniques, adsorption and desorption of nitrogen, argon, other fluids, which can give us insights into the pore size distribution, especially for micro and mesopores, and then mercury intrusion porosimetry at larger scale, plus the overall porosimetry using pycnometry. There's small and wide-angle X-ray scattering techniques which give you a different perspective on these materials. Through the X-ray scattering, we can see how the material is organized. And these techniques can be used beyond crystalline materials, but also to test disordered materials, to investigate how rough, for example, particles are, as we will discuss later on. I mean, this is an image here of a small angle X-ray scattering and wide angle X-ray scattering equipment in our own labs here at UCL by the company Xenox, previously Sachs Lab, and where you can even look in situ also at particle organization and at roughness over a very wide range of length scales. So all these techniques together can give you some insight into the materials, and these can then feed into models for porous materials. Yet another way is to consider that porous media, as I've shown with that example of gamma alumina, are very complex. And so we can use statistical descriptors. So, and this then is a way of relating the microstructure of the material to its overall macroscopic properties. So on the one hand, you have a microstructural characterization, which you can get via porosimetry, via X-ray scattering, and it can give you information on, say, correlation functions, the overall porosity, the correlation functions, chord length, density functions, cluster functions, and so forth, and then relate these to macroscopic properties. And this can be done via statistical mechanics, statistical physics, and many particle systems. And I put here a few references to books by Adler, Torquato, and Sahimi, and work that's been done. In fact, Keith Gubbins was one of the pioneers in this area to really use this type of descriptors of these materials. So you can then reconstruct a material of very complex nature based on imagery as well, 3D images, and then using a number of so-called Minkowski functionals. So they're the integral geometric measures, the volume fraction, the surface area, integral mean curvature, Euler characteristics, and possibly also Boolean methods. So where there is a pore or not, it's 0 or is 1 in solid material. So these are all ways, information that can help us to build a porous materials as a start. Now, why are we interested in all this? Well, I mean, personally, my background is in chemical engineering, catalysis and reaction engineering, as doubtlessly many of you. And often we have a challenge of how to relate what's happening at the nanoscale, the chemistry, and also the physics with what is happening at the macro scale. And there are several orders of magnitude difference in a typical chemical reactor, say in a chemical plant. This goes from the nanometer to all the way to the meter scale, that is 9 orders of magnitude. And so even though we would like to go through catalysis from some reactants through a reaction network to a desired product distribution, the intrinsic kinetics may be skewed as a result of transport limitations. Transport limitations within the porous particles, so just within the nanopores that are part of particles, and these particles are part of pellets, which are in a reactor. And so you can have transport issues overall, you get maldistribution issues, and all this will skew the overall product distribution. So a description of these porous materials is extremely important. And I'll talk about both the nano scale, at this nanometer scale, and also this micrometer, millimeter scale here, focusing on mesoporous materials. Now, key in this is that many of these heterogeneous catalysts that we use in industry or for automotive catalysis, environmental catalysis, but also for adsorption and separation processes, are nanoporous materials with very narrow micro and mesopores. Now, I put nanopores between quotes. The IUPAC tells us now that these are pores less than 1 nanometer. Personally, I find this unfortunate. I think the terminology, it really depends on how molecules interact with the environment, with the pore. So if you're a hydrogen molecule in a pore that's 50 nanometers wide, it may behave very much, as in the bulk, but things depend also on its mean free path, right, of these molecules. So whether something is affected by its environment really depends on things like the pressure, on the conditions, and on the ratio between also the size of the molecular probe and the size of these pores. So I would like to say that a nanopore for me is where molecules are almost constantly influenced by interactions with the walls, so that there are confinement effects. And so we certainly have this in this case in micropores, less than 2 nanometer diameter, but we often have this as well in mesopores, from 2 to 50 nanometer. So an example is Knudsen diffusion of gases in mesopores. So again, when we look at our particle and we zoom in, we have a network of pores through which molecules move. Now, within these pores themselves might be smooth, they might be rough. And so when molecules move, gas molecules move through these pores, depicted here in the cartoon-like fashion, we can have ordinary diffusion at high enough pressures when the molecules are interacting with each other. And this governs overall the Brownian motion and the motion of these molecules through the pores. However, even at atmospheric pressures or even at higher pressures, in many cases, if the pores are narrow enough, we are in the Knudsen diffusion regimes, where the mean free path, the average distance between two molecular collisions, is larger than the distance between a collision of the molecule with the wall. So, or rather, is smaller than the local pore diameter. And so as a result, you see something like this green or this red line where molecules are scattered from the walls and in this way move through the pores. So, but these materials clearly have heterogeneity at multiple scales. And so how do we categorize this? So we have those micro, meso, and macropores, and we are going to focus here in my talk predominantly on the mesopores. But then you also have the aspects of how the pores are connected to each other, which is a topological property. So this is connectivity of pores. And then you have aspects of morphology, which is the shape of the pores, the shapes of the, and say this includes also the roughness of the pore walls. So those are complementary aspects, topology and morphology. And so materials could also be isotropic, or they could be anisotropic with properties that change with direction. This is especially important if we look at rocks, geological materials, and so where anisotropy is more the rule than the exception. But many materials that we use for example, in membrane materials also are anisotropic. And then the porosity can be ordered or disordered. And so the model requirements that we have really depend very much on the application. If we're interested, as we are here, in transport of fluids for this talk and adsorption and desorption, then we need to have a model that allows us to study this. So the porosity also, if we have reactions that are involved, they could evolve. For example, due to catalyst deactivation with coke that is depositing in the pores, or you have mechanical transformation due to heat. You may have strain and mechanical aspects that become important so that the pore shape, size, the material properties really change, and that affects also the porosity. Then it becomes much more complex. So it is, as you see, I'm trying to cite here and give you a bit of a context for models. And so what is then a good model, right? Now, a model is always an abstraction. There is no model that is a perfect representation of reality, but what matters to us is that it is appropriate to our situation. And this is, perhaps I like to show this image here of René Magritte, the famous "Ceci n'est pas une pipe," this is not a pipe, right? It's beautiful, you even see the light that is shimmering in this, but it is a nice realistic representation, and yet it is not a pipe. It is a model for a pipe, it is a representation. Another example is Picasso's bulls, right? So it's a famous series he made over the holiday period in 1945 to the beginning of 1946. All of these are bulls. Some appear more abstract than others. There's gradually, he uses less and less lines. I mean, that's the mastery of Picasso here. He can depict it in a very realistic fashion, even though the most realistic images is not a bull, just like the pipe of Magritte is not a real pipe. And yet, maybe some of the aspects that interest us in the dynamics of this bull and its strength are perhaps very well represented in his most abstract depictions of it. It generates a type of simplicity, and yet it is also complex as a whole. So all of them are images of the bull. There is no good, there is no bad. It depends on the context. And so it is for porous materials. In porous materials, we have a variety of possible models. We could go all the way from atomistic models, which have become commonplace now to describe many microporous materials, whether they are zeolites, like ZSM5, or metal organic frameworks, where we really depict and are able, because of the crystallinity of these materials, to position all the atoms in space and have unit cells that are repeated over space. But then for many other materials, it is much harder to do this, especially disordered materials we'll get back to. There, Pore network models may be used, or particle-based models can be used. Those are examples of discrete models. And sometimes we have hierarchical porous materials which contain a combination of these. And then there is another level, which is continuum models. Continuum models where you homogenize this whole space, even though in reality it is heterogeneous. And then you have effective properties. For example, relating to our problem of diffusion and reaction, you would have effective race constants, effective diffusivities. And these effective diffusivities could be part of models like Fick's law with as a phenomenological law, relating the fluxes with concentration gradients. And of course, you could get more sophisticated chemical potential gradients or include Stefan Maxwell equations and such. But in a way, you are still creating an effective model of this whole heterogeneous space, including solid and fluid, pore space and the solid phase. And so this effective diffusivity needs then to be related to the diffusivities in the actual pore space. And so that would be DI here on the right. And the effective diffusivity is then related to this diffusivity through the fraction that is occupied by spores, so the porosity, epsilon s. But because the pores are not all straight, not everything is smooth, we also need to have a factor, tau, that is a tortuosity factor, put between quotes. And this is what much of this talk will be about, of how do we evaluating this. In fact, Rutherford Harris, very famous founder in our discipline in reaction engineering, called this a fudge factor already several decades ago, because it is purely a factor where we try to fit results, especially when we compare experimental results with theory, after we put in some value of tau in our reactor models and you know, to try to fit the data, right? And so, funnily enough, continuum models are actually, I would argue, the most complex. We would love to work with them. We would love not to have to model everything on atomistic level and every pore individually and put it together, because as I'll show, this can get really complicated. So we'd love to go there. The funny thing is that when you have a very highly performing machine and when you have the right quantum chemical models, the right interaction potentials, the atomistic models is what you'd really like to be able to use. But for many of the disordered materials we have, like the porous alumina I was talking about earlier, this gets quite hard. And this is why this is really important, of how we identify what is a good enough model, what is an appropriate model. But let's say something first to kind of situate this, what I mean with that. So the atomistic models, for example, could be used for zeolites, although also there you can coarse grain the description. You can coarse grain the description of this pore space and identify, say here, for MFI, silicolite as the pure silicon form, or ZSM5 with aluminum in it. You know, you have intersections I, you have zigzag channels Z, and straight channels S, right? And so, and then you can see how some of the sites in there, they're not silicon, they're aluminum, and they need to be counterbalanced, say, by cation in this way. And then you can start looking at molecules like CO2 and involve their quadrupole moments, and nitrogen with its quadrupole, and how it interacts with this environment, and perform molecular simulations. We've done such work. I mean, former postdoc David Newsom, where we looked at molecular dynamics simulations in this space, and where we were interested in seeing where the molecules spend most of their time. And interestingly, we find it's not necessarily directly related to the geometric depiction that you see here with these intersection zigzags, with these connectivities of 4 in the interaction channels, but we find an effective connectivity that's quite different in the sinusoidal channels, using at the basins where molecules spend much of their time. Say here 200 kelvins for 4 CO2 molecules, spend a lot of time there, and then they hop between them. We can use transition state theory to calculate rates in between them, and we find an effective network that is not necessarily the same as the original network we have that we see geometrically. So we have an effective coarse-grained network, and through that you can move from, you know, molecular dynamics via transition state. You can invoke kinetic Monte Carlo and look at diffusion over much larger spaces. And then you can compare this with experiments. And we can look at both self-diffusivities and corrected diffusivities. These terms, for those who were there, have been introduced by Professor Jörg Kerger in a previous seminar already. And so they may be different, right? And so because transport diffusion is not the same as self-diffusion. And so then we can compare these with experiments and indeed using Pell-Street gradient NMR or quasi-elastic neutron scattering find good agreement. Now, I show this example to show that in cases like this, we already have pretty good agreement in many situations and a much better understanding, especially for quite well-defined materials, such as this ZSM5 or the silicolite, especially if we have very good samples and we can compare them with simulations where we can go across these length scales. But even for zeolite, these microporous materials, there may be heterogeneity, which is beyond the chemical heterogeneity. There are defects, there are meso and macroporosity in it, either on the inside or outside. In fact, controlling this porosity is extremely important if we want to create membranes, as the elegant work of Michael Tsapatzis and colleagues, to make really, because the larger pores in between may control otherwise the transport. And the barriers in between these crystals, both in catalysis and in membrane operations, may actually dominate the overall transport. So these surface barriers have become an area of great interest. So this is one reason already, even when you invoke zeolites and my typical quintessential ordered microporous materials, that invoking heterogeneity and being able to model that is important, and where even meso and macropores will come in, because in many cases you're talking about hierarchically structured materials that contain such zeolite crystals within a larger particle and palette. And so when we get back to our images about, and we speak specifically about disordered materials, this is why we have a broader range of models we need to use. We have these discrete models. They can be discrete particle models. This is an example from the work of Enrique Iglesia and colleagues, where they looked at a palette containing particles, and then they can start using kinetic Monte Carlo simulation to look how diffusion happens through the pore space in between these little spheres. And you can have a particle size distribution even, and looking at situations where the mean free path is either much smaller than the average chord length here, or is of the same order of magnitude or larger, hence bulk diffusion or Knudsen diffusion, and start to see whether this tortuosity and how it depends on the effective diffusion properties on the conditions. Or we can use explicit pore network models. You see an example here on the right of some of our own work. Or we can go to continuum models, which doesn't mean you necessarily have the whole space as a continuum, but you can subdivide it in different areas so that you can include areas of various local properties, perhaps informed by magnetic resonance imaging, say, where the local porosity might be different and the local transport properties are different. And then this can help to optimize these materials as well and optimize their overall geometry as part of maximizing, say, overall yields in a catalyst pellet. Or you go further, and we have synthesis mimicking models. I cited the work of Keith Gubbins and Lev Gelb earlier already, who pioneered this area, and where you can really try to see how you can mimic the formation of these materials, different types of Vickers glasses or porous carbons or silicas, and control the pore space. So hence, if we go to porous catalysts, which are so-called amorphous, not crystalline materials, amorphous comes from the Greek and really means shapeless, but they are not necessarily shapeless, as we will see. We can characterize, using this variety of experimental methods, the pore space as well, and the surface roughness even of these materials. And so if we look back at our image of a catalyst particle, we have on the one hand the pore network, which says something about the topology. And these pores might be, say, cylindrical pores or spherical pores, or they might have a certain degree of roughness, and they might contain catalytic and adsorption sites. And so we can zoom in again and invoke how the molecules are interacting with the surface, and where perhaps small molecules can see much more of the surface than larger molecules, which can't access the whole surface. And as we will see, this has an important aspect, important influence also in transport properties. So this is a factor of morphology. It is really about shape. So it is combining the overall description of these particles is a combination of looking at how pores are connected, or how particles with their pores in between are connected with each other, and then shape factors, which are related to morphology. So let's now first look at individual pores and look at different types of pore models. These have evolved over time as also, we evolved from simpler, of course, descriptions to more complex one, but also because more characterization methods have allowed us to gain more insights in these materials over time. So the most primitive, if you want, models, but the most often used still today are parallel pore models. I mean, there may be even cylindrical models, all in parallel with each other. You can then invoke some degree of tortuosity, and even Wheeler already did this at the beginning of the 1950s in his famous series of papers in advanced catalysis, looking at diffusion and reaction in porous materials and looking at the effect of diffusion limitations. And then we can invoke furthermore also the roughness of pores. This is something we looked at, and this area is very close to my heart. It's something which goes back to my own PhD thesis work, which you'll see something back from later, which involves surface roughness. The fact that pores are generally not smooth, but that our imaging methods and X-ray scattering techniques and so forth tell us that these materials are rough and that we therefore should look whether this roughness has an impact on diffusion. And then we have, of course, atomistic models. And so going back actually to the types of diffusion, as already mentioned in these mesoporous materials, you can have molecular diffusion within the pore space, but also often for gases, Knudsen diffusion, there where the mean free path is approaching or is larger than the local pore diameter or the local chord length. And I cite here work that is dating back from the 1940s, right? Because it's still relevant. Pollard and Present, in fact, did analytical work on the diffusivity as a function of the ratio of a tube radius to the mean free path of these molecules, and showed how the normalized diffusion coefficient, so the diffusivity related here to this factor of the local pore radius and the average velocity of the molecules relates with this ratio of A over lambda. And you have then an approximation derived by Bosanquet, which is extremely simple. It just says that you can add resistances. So instead of conductances, you have the resistance. The inverse of the diffusivity, in effect, it is an effective diffusivity at the pore level, is equal to the inverse of the bulk diffusivity, the molecular one, plus the inverse of the Knudsen diffusivity. And as you see, with this analytical formula, it has a really excellent agreement. And this was actually verified years later also with molecular simulation. So very good agreement. This law is often, can be invoked, particularly when adsorption on the walls is not as important, I should say. And there are some other effects that may play a role when this formula breaks down. I'll get back to that. So a way then to use this model in practice to calculate an effective diffusivity in a material, if we go back to the simplest models of parallel pore models, tortuous or not, is to calculate an effective Knudsen diffusivity, if it's for pure Knudsen diffusion of gases, using Knudsen's original formula, but then corrected with a porosity and a tortuosity factor. And so here, the average velocity would be the square root of 8 times the gas constants, the absolute temperature, divided by pi, and the molecular mass of the gas. So the heavier it is, the slower the diffusion, as you would expect. If the pore is wider, the diffusivity will be higher. If you include Knudsen and molecular diffusion, you can include a pore size distribution as well. And if these pores can be considered parallel, you can easily integrate. And then the tortuosity here invokes other facts of the pore tortuosity. However, this assumes a parallel pore model. And so using this in practice, often one assumes some type of relation, that fudge factor, as Aris called it, for the tortuosity. But through many types of, both experimentation and some types of models, it was found that you can find relations between the tortuosity and the porosity of these materials. And oftentimes a simplified power law relation is used. You find it in Wakow and Smith's work in the 1960s, or Bruggemann's going back even to the 1930s. Even to these dates, this is what's typically used, if not even a constant factor like 3 or 4. But it's often quite arbitrary, these factors, as we'll see. So unless there is a clear indication to assume a particular geometry, it's actually quite dangerous to do that. So you could use a model if you know through synthesis that it's just an aggregation of platelets, an aggregation of pseudospherical particles, then you can use models based on, say, stacks of spheres, overlapping or not. And indeed, you have relations then in this case between the tortuosity and the porosity. This goes back even all the way to Maxwell in the end of the 19th century, who studied these type of relationships and finds relation between tortuosity and porosity. However, if you don't know that, such correlations are really best to be avoided. Again, there are exceptions where we have insights in mesoporous materials and where the situation could be simplified. An example is the ordered mesoporous materials, like the MCM41s, 48s, or the SBA family of materials. There, through experimental characterization, we know something about the local pore diameter, they're well ordered, and we can use such models. There's elegant work by Doug Ruthven and colleagues that they published in 2009, where they wanted to test simply Knudsen's simple model using the type of formulas that I showed earlier for a well-defined mesoporous silica membrane. So it needs to be a well-made material with a clear here, a unimodal distribution of its pores here. So the pores are neatly around 5.4 nanometer. And then indeed, you have a well-characterized material and you can use these formulas for the Knudsen diffusivity, like the ones I showed here, right? And use this model and test it, experiment with modeling. And indeed, Ruthven finds that we can be comfortable and that these models fit the experiments luckily quite well in this situation. Another situation where we can go and have a good insight in the material and can gain more insights goes back again to atomic description of the materials, which, as I said, for zeolites, you can do relatively easily, but for mesoporous materials, this has only become possible in recent years, right? Here, using supercomputing techniques, my former postdoc, Kasia Maksimiak, looked at the construction of such a mesoporous silica, like an SBA15, even with a pore of 5 or 6 nanometers, and really relaxed these models of these mimicking in a way the synthesis of these of the silica, and taking also care of the proper charge distribution. If you want to use this material, say for a liquid environment, in this case we looked at a liquid with enzymes, and we were interested in the absorption and the transport of enzymes in these pores. So this is a very, very involved simulation. You can look at a single pore in this case, and you could really go fully atomistically and simulate already how this enzyme is interacting with the ions and with the roughness even of this pore, and correlate this with things like the zeta potential, so you get the right charge distribution and so forth. So I would say this is where we are in terms of the state of the art. But if in most cases of mesoporous materials, it is still extremely hard to do this. And is it even necessary? So again, using the image of Picasso and his bull, where should we place ourselves? So as we'll see, the purely smooth pore will not be enough. We may need to include roughness. We may need to include also the topology, the pore network connectivity in materials where the pores are connected. They are not all parallel to each other. But how do we do this, and how important is it? So let's now look at the single pores, right? So it was shown already in the 1980s by David Avnier, Farin, and Peter Pfeiffer that many porous materials, they're a bit like the coast of Norway, right? I mean, to paraphrase Jens Feder, they have this fractal surface roughness. So this is at a macro scale, the whole coast of Norway or Britain, where you have fjords upon fjords upon fjords. And so the length of the coastline depends on the resolution at which you're looking. The same thing happens even for porous materials. You zoom in on the porous material of an alumina particle, and it becomes rougher and rougher. The surface area depends on the size of the molecular probe, and you also have a fractal scaling law, where the fractal dimension now is a number between 2 and 3. For a coastline would be between 1 and 2. So if it's 2, it would be smooth. 3, it would be a volume filling surface, right? And both happen, and you can have everything in between. There's a bit of a cartoon here of what you have for a porous alumina based on all these aggregates, but they actually are rough. And so this is a much more realistic model, and we should see how we account for this. And this was actually the subject of my PhD work. And we looked at that time with X-ray scattering. We couldn't do it in our own labs. We have to go, and we collaborated with both with Shell and with Institut Langevin to do small angle X-ray scattering. And we could look over a range of length scales and indeed found that the surface of these pores is indeed fractal on ranges that go from a few bond lengths within the alumina all the way to the size, of the average pores, which was around 6 nanometers, these mesopores. So they really are fractally rough, which is not something you can easily see with adsorption experiments to have to cover that whole range. And so accounting for this then would be important if you're interested in something like catalytic reforming using that type of catalyst. So if you then zoom in, well, a molecule will see this roughness of the surface. And if you are, say, in catalytic reforming, you have gases. And so these gases molecules collide with the pore walls, interact with the pore walls. And so as a result, the first passage time for a molecule to go through a single pore with its rough walls or through porous material, that first passage time will increase from a T0 if the pores were smooth to T, which is larger than T0 if the pores are rough. And so how that depends and how that first passage time changes depends on the accessibility distribution. And so you can derive an analytical model, which is what I did, and find a relationship between the Knudsen diffusivity as a function of the diameter of a molecule. The prime here is divided by the so-called outer cutoff of the fractal scaling regime, which for this alumina would have been 6 nanometers, right, in the example I showed. And this is divided by the one if the surface were smooth. And so you have something with two parameters which depend on the fractal dimension and another parameter depending on the shape of these of the roughness alongside the walls. So what does this mean? So when you do this, you essentially, this is like if you had a smooth channel, but you have certain waiting times alongside it. And so you have a certain time also in between different collisions or going within these indentations. So you can construct then computer models of these channels to investigate this roughness. And this is something my former postdoc, Kourosh Malek, did several years ago, where he constructed fractal self-similar models of different degrees of roughness. So 1 generation or 2 generations or 3 generations of further having more and more roughness, right? And that would correspond to a surface that a small or a larger molecule would see. And so when you do that, you can perform kinetic Monte Carlo simulations of gases and compare them with this analytical model being the line. And we got pretty good agreement between the kinetic Monte Carlo simulations and the experiments. And as you see, indeed, the Knudsen diffusivity normalized towards the one with smooth walls depends significantly on roughness. You see the factor is quite significant. So this is kind of a summary of this, of dynamic Monte Carlo simulations compared with the original theory where you get good agreement. But then this was the beginning of this century. Now move forward to the current age. And so in my lab, we built this equipment with ultra-high vacuum diffusion setup. This is inspired actually by the original experiments of Knudsen himself in 1909, and really the pioneers in this field, which is clearly that they were interested in vacuum equipment. This was also the birth of quantum physics, which propagated these interests in these studies. And if you are at very low pressure, clearly the diffusion of gases is dominated by collisions with the wall, right? The mean free path can be meters long, right? And so we constructed this out of 2 vacuum pumps with a pipe in between, and we can control independently with turbomolecular pumps the different pressures in this and control the flow through this. And so so this was built by a former PhD student, IU, and then recently my student Maria, then she investigated how you can construct different 3D pore models using 3D printing. And so you see that this is the same model we had as the model we took that Kourosh Malek used for our kinetic Monte Carlo simulations of diffusion, which allows us to compare directly the Monte Carlo simulations with experimentation. So it's like a blown out mesopore. So it's blown to macroscopic scale, and it's a geometrical representation of what is happening at this nanoscale. And so we recently published this in a special issue of another one of the pioneers in diffusion and reaction, porous catalyst, Klaus Jensen from MIT. And so Maria did experiments on this. And so this is basically the answer of a 30-year journey for me, which really, so this shows this 3D printed image based on CAD, different pores of different lengths. And what you see here is the diffusivity measured. These are the blue points, the computational results for kinetic Monte Carlo in red, and the analytical theory, where you see that we have experimental validation. So this to me demonstrates that it's really important to include this surface roughness, which was very hard because to test directly on porous materials, because these disordered materials, typically, they don't have all these parallel pores. So you have to include topological effects, and you may have other factors that play a role overall. The heterogeneity is difficult to control. So using a model like this can give us fundamental insights, which you can then use overall in pore network models. So does this really matter? Well, it matters really all the way to the macroscopic scale, even industrial scale of reactions. So going back to that platinum rhenium on alumina catalyst used in catalytic reforming, I predicted years ago that the hydrogen yield would depend on the degree of roughness of the surface. So you would have a maximum as a factor of the as a function of the fractal dimension. If the surface is very smooth, you have a low yield. If it becomes rougher, you have more access to the surface, but the diffusivity becomes lower and lower. The Knudsen diffusivity, at least. Hydrogen can get trapped also, and this can lead to selectivity issues, where it can overcrack desired molecules in the catalytic reforming. And that is why for too rough surface, the yield of hydrogen goes down. Okay, so this is just an example of why this matters. And what I'm really excited about is that now we can control these pore roughness. So something as a side note that I want to mention to you is also that pore length has an important effect on Knudsen diffusivity. This seems to be often forgotten, even though this goes back to work of Clausing in 1932 and even Dushman in the 1920s. Right? There's a certain transmission probability, FT, of going from one side of a channel to another side. And this was tested in their case with vacuum experiments and with theory. And so just to show you what effect this is, if the length of your pore would be the same as the local pore diameter for a cylindrical channel, then you're over-predicting the real Knudsen diffusivity by more than a factor of 2. And yet, this is the type of model that's often used even in pore network models. So one has to be very, very careful. So even on simple pores, cylindrical pores, be careful what model you use for the Knudsen diffusivity. Now, if you go back to that image I showed earlier of rough pores, we can coarse grain that whole image and consider this as a channel with effective heterogeneity. That could be geometric, it could also be chemical. So there's a more general model where you can consider a channel with traps on the sides. And that's something we proposed in this paper in honor of John Prausnitz, in fact, published in 2006. And very recently, this was compared with experimental work on Knudsen permeance experiments through mesoporous inorganic membranes by the group of Rezwan and Heuming and colleagues. And so they constructed these mesoporous membranes with brush structures on them with different functional groups of different lengths, and found that the Knudsen theory needed indeed to be corrected. So in this case, it's not just geometric roughness, but it is also the interaction of these molecules and how this leads to extra trapping alongside the walls. And so they show good agreement with that model that we proposed several years ago. Another aspect on the that goes even deeper in fundamental theory that I want to highlight is the work of Suresh Bhatia and Nicholson, who have done a lot of fantastic work in this area, looking at mesopores, they have this so-called oscillator model. It would take me too far to describe this to you, but I refer to their papers here for you to check in more detail, because what they mention here, that is, even if you have a smooth cylindrical pore, you can have actual momentum gain between different diffuse wall reflections, and you may need to account for that. So in certain situations, you really need to account for that, and otherwise you get disagreement between purely geometrical models and these more physical chemical models. And they validated this both with equilibrium and non-equilibrium molecular dynamics. So if we go back to our model here of these porous materials, I talked about morphology, but let's say a word here now about topology and think about that tortuosity factor. So is that tortuosity factor relating to that image I showed earlier by Enrique Iglesias and colleagues and Reyes, is the tortuosity factor really a constant? That has been debated by many. Already in the 1980s, there were models including diffusion and reaction, and where they said, well, reaction kinetics may play a role actually in this tortuosity. So that already shows you shouldn't just, it's not just a geometrical factor. Then it was debated whether diffusion mechanism plays a role. What Zalk, Reyes, and Iglesias showed through their kinetic Monte Carlo simulation, that luckily it's independent of whether you have Knudsen or molecular diffusion. However, their model did not include the roughness that I actually demonstrated to you plays an important role. So one has to be careful. It all depends on the type of material. If you have smooth enough spheres or that roughness is on small scale compared to the pore channels, that's fine. But otherwise, one has to account for that. And again, let's not forget older work that sometimes seems to get forgotten. Fundamental work by Desjardins in the then Soviet Union. But look here in English also in this paper here, Progress Surface Science in 94, there's an elegant theory he derived on the base of chord length distributions. And he showed really simply that if you have diffuse reflections, so a cosine distribution on the walls, which is also what Knudsen assumed, and you have, say, an exponential chord distribution, not too, which often happens, by the way, like in the situation here in this model of Reyes and Iglesias, then the tortuosity veers towards a constant. It becomes approximately 1.44. That's really an analytical model they were able to derive. And so that's really a reason why these tortuosity factors tend to be around less than 2, right? And so so for this type of materials. In other cases, again, you will have to deviate from that. And so there's a whole range of pore network models that go into the details of including intersections between pores, full pore network models with pores that, of different pore sizes. And sometimes the older models would include narrow pores and broad pores, calling them micro and macro, but they might actually be mesopores that are narrower or broader. If you have beta lattices, so no network effects, no loops, but just a tree-like network, like in this beta lattice, again, you can analytically solve your equations. That's shown in this paper by Sahimi, Gavelas, and Tsotsis, which is a very beautiful review paper I will mention and relate to it at the end. Voronoi tessellations, but now more recently, there are also pore network reconstructions based on X-ray microtomography and even nanotomography from porous materials that can help you reconstruct the pore space so that you have truly input to what are otherwise rather artificial pore network models like the ones under C here. And then we can have pore network cutting algorithms, something like my former PhD student Guanghua Ye, also in collaboration with Professor Zhou Xingwei in Shanghai, has worked on where we can construct all kinds of pore network models for a catalyst representative of catalyst particles and pellets in different geometries. So here I can't talk about all that in detail, but I'd like to highlight the work of Lynn Gladden, again pioneering work in the early 1990s, where she really looked at pore network connectivity. And it really demonstrated that even with simple models, you can already see quite a bit. You can find out, is it important to include this connectivity? Is it not important? When does it become important? Is it important that the pore networks are regular? Or should I really include the randomness of these pore networks? That's what they actually were testing here. And so what you see here is the conductivity. So it's like a diffusivity, okay, of this pore network as a function of the probability P that, say, a pore is so if you have a lattice model where two nodes in this lattice, they are connected or not. So if everything is connected, you have 1. If nothing is connected, it's 0. Clearly, if nothing is connected, there's nothing conducting. If everything is conducting, they normalize the results to 1. And they want to see as a function of the connectivity when they turn, in a regular or random network, some channels on or off, so they're conducting or not. How does the conductivity depend? And so let's look here. So we have this percolation threshold in green. So a percolation threshold, what that means is that if you have a network like this, if very few of these channels are occupied, then the whole material is disconnected. There is no conduction. If enough is connected, then you have conduction. And then there's this critical point, right, around which the system actually becomes self-similar, becomes this fractal self-similar structure where you just have conductivity. That's called the percolation threshold. And so renormalization group theory has to be used if you want to look at conduction around these points. And the classical theories do not hold because of long-range correlations in the system. But going back to Lynn Gladden's work, what she showed here is that both for random or regular networks, if the connectivity is high enough, and that's even in the case of connectivity of 6, so cubic network, you get similar results, except if you're really close to that percolation threshold. Now, if you go to a connectivity, on the other hand, of 3, so much less connectivity in the system, perhaps because this is a porous catalyst that gets deactivated, or there's structural changes due to solid reactions, then things start to become different. Whether you are random or regular plays a role, and you clearly have a much more impact on the overall conduction property. So what is a good enough model will depend on your situation or how connected your pore space is. And an image like this can already show you what that means, how connected it is, right? And what she also showed with a former student, Michael Hollowand, is that if you just take a classical model where you have, connected pore spaces, and you assume that some of these links, they are connecting and some are not, when you have a very low fraction of, micro void, as she calls it here, then you get these extremely high tortuosities. You can get factors of 100 or so, especially when the connectivity is low. These numbers are clearly unrealistic. I mean, they are not being measured. And the problem is that a lot of the pore network models, as they were used, and quite a few still used today, they are so-called one-level pore networks. This is not what you see in reality. Typically, you have an image like that where you have several levels. You may have a palette that consists of particles, so with macropores in between, and then you have the mesopores, or you have micropores, even if it's a zeolite, say, inside these crystals, inside the pores. And so it's really important to include these two levels. You can't just discard that, or you get totally unrealistic levels. And so again, what she showed here is that an effect on these tortuosities getting much more realistic results, and also demonstrating the importance again of the connectivity in these materials. Okay, and so a theory I want to highlight in this context is the effective medium approximation, or EMA theory, which was introduced by Bruggeman already in the 1930s and then generalized to pore networks by Scott Kirkpatrick in the 1970s. And so what's very elegant in this is that you have these pore networks or channels of resistors or conductors with a certain conductivity G. And so you assume then that you keep the whole topology of that network, but you're going to replace all these conductivities by a single value, GE, and you call that the effective conductivity. And if you do that, you can solve this equation here. It's an integral over the conductivity distribution, which is related to a pore size distribution. So if these are pores, you can have models that relate to the local diffusivity and the diameter of these pores if it's a cylindrical pore. And so you can actually calculate the effective conductivity or the effective diffusivity, including the connectivity C of this network. So this is a very elegant theory, and it works incredibly well in many situations, especially if you're far enough from the percolation threshold. So if you're really a poorly connected network, low connectivity, and you're close to percolation threshold, this theory breaks down. Now, what Bourganos and Sotirgos did, and I think this is brilliant work and dates from the 1980s, but what he showed elegantly is that if you combine EMA with a so-called smooth field approximation, so this means that you are going to assume an effective theory where the pores, it is as, you replace the connected space by some effective mean field model for the pore space. And so that means that you can even calculate that this tortuosity in that effective space would just be 3 in 3D. In 2D models, it would just be 2. Then you can use the EMA on that in combination with the smooth field approximation. That gives you extremely good representation. I want to show this work by Stratis Sotirgos, who sadly passed away much too early, driven over by a drunk driver in Brussels once at an EU meeting. And he shows you how the effective diffusivity, both for bulk diffusion and even with Knudsen diffusion, if you combine effective medium approximation with a smooth field approximation, and you compare these broad variety of pore networks with Monte Carlo simulation, you get really, really good agreement, except in some very narrow range. Zhang and Seaton went even a level further and used continuum theory, comparing it for realistic models with a pore network model. And so if you have good connectivity and even chemical reactions, they find, again, that you have pretty good agreement. But what is highlights to me is that you need good models at the pore level. Yeah, so you need to include morphology, because what none of these models does is including morphology. They assume typically smooth, long cylindrical pores or spheres in other situation. They don't include the morphology. But topologically, there's a lot of work out there that dates back already from the end of last century, that some of it seems to be forgotten. And so this is something that we have included in our IUPAC report to remind people. I won't discuss this in detail, but there's also the dusty gas model, which allows to include you also surface diffusion and other factors. And I refer to that, the book of Roy Jackson, which is all about that, but it's also summarized in our review paper. And then you can go further and use computationally assisted design for hierarchically structured catalysts. This is something, again, that I worked on with my former student, Guanghua Ye, who is now an associate professor in East China University of Science and Technology. We can create these pore networks in arbitrary shapes, look even at multiphase reactions, at deactivation over time, and look at hierarchical pore network structure optimizations. All this can be done nowadays. To give you just one example, to finish here, is catalytic hydrogenation of benzene is a multiphase process. So what I showed earlier was all gas phases or single phase situation where things are simpler. But if you have a multi-phase situation, you may cross this percolation threshold in points, because in this reaction, you will have condensation of molecules, or the pores become very narrow and you have capillary condensation of the pores. So they're only partially wetted. So you need to include these effects. So I won't go into details of this, only to tell you that you have what won't surprise this adsorption community. You have hysteresis phenomena of adsorption and desorption, just like you have when you investigate materials with nitrogen adsorption and desorption. And so this needs to be included in these models. But we can do that. We can construct pore networks, evolve their geometry, calculate mass transfer and reaction, and calculate even phase changes. And just to show you one example of where we were able to do and compare with experimental results, we show that if you have to use a continuum model, you don't get as good agreement with the experimental results as using a discrete model for the effectiveness factor for this reaction of benzene hydrogenation as a function, in this case, of the bulk pressure of benzene. This matters because if you increase the pressure, you will have increased condensation. All right, and these pores, so you have capillary condensation effects. And so you get hysteresis effect when you increase and then decrease the pressure. You are moving through this hysteresis loop. And so we were able to get excellent agreement between experiments and theory. So, also the effect, like Lynn Gladden already said, you need to make sure that you have the right network. So not just single level, but two level. These lead to different results. And so this will play a role here when you have condensation evaporation results as well. So finally, to end where I started, we need to be able, or we try to move towards a situation where we can correlate the synthesis of materials to the models of these materials, say for a material like gamma alumina. And this is something that I'm very interested in, and we've been working in the context of a Eurokin consortium, sponsored by Albin Marley and Johnson Matthey and IFP, Énergie Nouvelle, who've been interested for a long time in how our elementary crystallites relate to the final morphology and the structure of porous alumina particles. And so this is clearly important to construct models for diffusion in them. And so recent work, a seminar would not be complete nowadays if you don't mention machine learning and AI tools. And indeed, we looked at images of these materials, and they are very heterogeneous also at a macroscopic scale. So these aluminas, if you have cross-cutting sections here, you see a matrix with some particles inside this matrix, and they may have different local tortuosities. And We measured this also using pulse-free gradient NMR and constructed models to compare this. And so in order to characterize these materials, we really need multiple techniques: adsorption, desorption, even cryoporometry, imaging techniques, mercury porosimetry, X-ray scattering. Only that gives you an idea. It's like that image of the cow and, you know, or the elephant and the parable of the blind people, you know, touching the trunk, touching the legs or the trunk of the elephant or the hair and thinking, you know, it's this shape or it's that shape. You need a variety of techniques. And so we found indeed that different alumina supports, they have entirely different structures. They may have different tortuosities. And even if they have similar local porosities overall, you know, as you see in this data below, still the overall diffusion properties may be different. And so hopefully this will excite you to show you that we have a new frontier here, that is not just in zeolites, but actually also in mesoporous materials between the matrix and these inclusions. When you look at these alumina plates, also there you have interfaces, and they may influence how molecules are moving inside and outside. So there's really a new frontier here of studying these surface barriers, which again then would need to be included also in models to explain the properties of these materials. And this is an industrially used material, right? So to end here, what is the best model? So clearly characterization methods are increasingly sophisticated. They will give us a lot of information, but we don't necessarily need all of it. We need a good enough model for our purpose. Every model is an abstraction of reality. We need one that's appropriate for our purpose. And so depending on the circumstances, you may need a pore network model, you may need an atomistic model, or you can deal with a continuum model. It's a bit like the, you know, Picasso's bull. It depends really of what you want to highlight in that bull, which features. The essential characteristics will depend on the application. Clearly, we have more and more ability to use atomistic representations. Sometimes they are needed, I would say. In other cases, not. But we can use them, also parameterized by these new characterization techniques. So here I want to advertise here our review paper. That was the basis. This was by Brandon Bukowski, Frederik Keil, Peter Avikovic, Germain Sestre, Randy Snur, and myself. They appeared in Adsorption Journal in 2021 as part of our series, and which informed also a IUPAC report. And so you will find many, many more details in this subject for micro, meso, and macro pores. And so Professor Jorkager already showed this IUPAC a technical report that he led on, and which I was honored to contribute to, about diffusion and nanoporous materials that discusses and highlights the importance of relating theory with experimentation. So I want to thank also the funding for these aspects of my work from Eurokin, different industrial partners that have supported us to look at porous materials. And I feel in the end, I want to acknowledge, I always acknowledge members of my group throughout my presentation, but this presentation to me is very special. I especially prepared it for you and for this occasion. And it goes back to my earliest step in research, okay, when I was an undergraduate student, a junior undergraduate student. And the first paper I was given to read by Professor Gilbert Froment, we became my master's and PhD thesis advisor, was this paper by Mohamed Sahimi, George Cavallas, and Theodore Tsolitz. And I found it a brilliant paper that really inspired and excited me about, you know, statistical and continuum models of fluid-solid reactions in porous media. So I just want to highlight this here. I mentioned it earlier, and it still contains a wealth of information that is useful to this date, but becomes more alive now that we have these new characterization techniques to inform these models. And also for Kyle, I've collaborated with over the years. I mean, we have a nice review related to microporous materials, to zeolite. But then, you know, his paper on modeling of phenomena within catalyst particles, where in fact he refers to my original work in 1996. So I'm really grateful to him and for the wonderful collaboration we've had over the years. And clearly the book by Jörg Kerger and Doug Ridvan, who, you know, was really inspirational to me in my journey on nanoporous materials and zeolites and diffusion, and where I've had the great pleasure and also, you know, to be inspired by this work by Jörg and Doug, who sadly left us too early. And you know, it's been an interesting journey for me from the first conference on diffusion fundamentals in Leipzig in 2005, which I had the pleasure to participate in, and where I met Jörg Kerger for first, to a series of diffusion fundamentals conferences, Jörg mentioned them in his previous talk, and Jörg became, a collaborator and a great friend over the years. And I've been honored to take part also in the Saxon Academy of Sciences. There's a picture of us just 2 weeks ago with Jörg in the Academy of Sciences, where I presented also on some other aspects of our work, and which has been, also supporting these diffusion fundamentals conferences over the years. And so I want to highlight the newest one, the 11th one, which will be held and chaired by Randy Snur. Even though I'm sadly, due to really other circumstances, I won't be able to attend myself, I really recommend you to go. It's been an amazing conference over the years that really links people from a variety of disciplines around this topic of diffusion fundamentals that's so dear to this. So with this, I'd like to thank you again for listening and end my presentation here with this overview of this IUPAC technical report. Thank you very much.
Thank you, Dr. Marc-Olivier Coppens. It was a really interesting talk on diffusion in mesoporous materials. We have a couple of questions. I'll probably relay them to you. The first question is there a way to determine either experimentally or via simulations to understand whether a gas is in the Knudsen diffusion phase or it's an ordinary diffusion phase within the micropore?
So your question is whether there are a way to determine whether you're in the Knudsen diffusion phase or in the normal diffusion.
Yes.
Is that it?
Yeah,
well, that is completely related to the mean free path of the molecule. So for a gas in the Knudsen diffusion, the mean free path, which you can also calculate, and it can be related to physical chemical properties of that fluid. When the mean free path is much larger than the local pore diameter, which you would get from a pore size distribution measurement, then you are in the Knudsen diffusion regime. So you can clearly directly measure diffusivities and measure them for various conditions, say various temperatures, various pressures, so that gradually you change the mean free path. And you would see then this transition going from the pure molecular to the Knudsen diffusion regime. However, in mesoporous materials with a few nanometers in size, even at ordinary pressures, you will find that the mean free path is typically larger than the local pore diameter. And so this Knudsen diffusion becomes even the dominating one.
Yeah, okay, makes sense. Thank you. Then the other question, one other question we have is, what are the challenges in performing these accurate experiments to estimate the diffusivity of, let's say, CO2 into porous materials? Because we see that the match between simulations and experiments are perfect. So are there any challenges involved in both the simulations and experiments to get?
Well, are they perfect, right? So that is actually a good question. I'll show you some examples where you have good agreement. There are other cases where there are factors that are unclear. So sometimes you might even get agreement, but you model it. It's just because you model it with a fudge factor. You put in a tortuosity, and it might seem good enough because if you look at this diagram here between molecular Knudsen and the severely confined, say in a zeolite, you have orders of magnitude difference of diffusivity. So there you clearly can't get away with it. But here you might say, well, it's only a factor of 2, 3, 4, right? So if you just put in a tortuosity that is large enough or small enough, you might be able to fit your data, right? You might be able to fit them. But if then you are going to use that same model under conditions with reaction or under different conditions or different molecules that you use, which perhaps see more of the surface or less of the surface, there it comes into play that you really need to include the morphology of the surface, which is something you have probes that are different, say, under your practical application, whether it is in your membrane or your reaction condition, as the one that you would have under the computational condition. So one has to be really careful that you have representative experimentation. So both the topology, as I highlighted, and the morphology can play a role. If a catalyst is deactivating over time, right? So I mean, this is just an image here on the right. Just a snapshot of a simulation, but over time, what is accessible of the inside of that pore space will change, right? And this is something to really difficult. It's much harder to test experimental. There's more and more insights now with molecular probes and going into porous materials, but the majority of the work is still on zeolites, and maybe some on MOFs, microporous materials. And what I tried to show you here is that even for mesoporous materials, you have some exciting things happening, and that has not been studied as far as I know. So that there are these type of effects. And so just like Yohi Denayer, Gino Baron, Jörg Kerge, and colleagues have demonstrated a number of years ago, if you start to look at a bag of zeolite crystals and you take out different individual crystals, you find that the transport properties are different. The uptake is different due to surface barriers. And we have also shown how you can modify these surface barriers in our work. So it becomes really important. But earlier work, while skin effects were even proposed by Kerge and also by Berger in the 1980s, there was no way of directly measure that until now. Now we see these effects. So even these fudge factors that we use, they might work on interpreting one set of experiments, but if you extrapolate and you use this for design or to interpret others, you will be off. That is the problem. So you might see an effective diffusivity model that seems to work, but you're actually hiding the reality because you use simply that tortuosity to cover topology. It's more than in zeolites because you have topology, surface barrier effects, morphology, roughness, all these things are all combined in one. Yeah, so that's the reason why proper modeling is important, especially if we go for rational design, which is something we like to do for zeolites and MOFs. Why not for mesoporous materials, which are used in at least as many practical situations, I'd say, as the zeolites, right? Why not use it there?
Yeah, true. Yeah, I agree. And we have a follow-up question on that. We see that the tortuosity is not a good way to generalize the surface roughness. The question is, are there scenarios or materials where it works well?
Where the tortuosity works well, you said?
Yeah.
Sure there are. So, again, my, favorite, analogy, of this bull, it depends on the situation, right? So if you go to your different types, I mean, this is a sketch of different situations. Yeah? So if you have a porous material that is uniform enough, say it consists of, say, nice alumina particles in this case. Could be zeolite crystals or alumina particles in this case, a mesoporous material. And it's a single phase, gas phase, or even single phase liquid phase. And porosity is well connected. There is no reason to use, I mean, there is no reason. You can get away with a continuum approach where you can use a tortuosity. And so the work of Zhang and Seaton already in the 1990s showed that if they compare a model with explicit pore networks and such and compare it with a continuum, you get very good agreement with it. You can fit a tortuosity to it and it works really well. It is when percolation effects start to play a role, when you have multiphase situations, when you start to have surface barriers, then it is really important. And I would actually add to that, if you do rational design, if you start to optimize materials, which is something I'm doing in my group, also using this nature-inspired solution methodology to try to see how you can get the best materials that have optimized yields or selectivities and such, then you start to see that you displace the issue, right? So you can start controlling surface barriers, for example, and in this way modify that. And if you just use an effective model, you're not going to demonstrate, you're not going to find that. You're not going to be able to guide that. You're not going to have the ability of this rational design. Yeah, it's the same with the roughness. You can put it in a tortuosity, but if you want to actually design better catalysts, perhaps this is a parameter you can play with, the roughness, so that you can modify the tortuosity. So for design purposes, it's a really bad idea to use just that fudge factor, you see?
Okay, perfect. Yeah, thank you. And the next question we have is, in a general adsorption process, we're going to have like multiple gases. So how do these individual gases influence each other in terms of their transport phenomena?
Absolutely. It's a great question. And I did not get into this. Most of what I said, I talked about, look at the model that's here. I tried to keep that part simple because there's several levels of complication. And this is an excellent question. The reality is that typically we have a mixture of gases. Of course, if you are in the Knudsen regime, the gases don't see each other, right? So since it's governed by collisions of the molecules with the walls, is dominated by this. So, Knudsen diffusion of a mixture is the same as, the individuals. Yes? So at low pressures also, that's what you have. But if you start to have multiple components, then there is a description. I mean, it's a Stefan Maxwell description of diffusion, multi-component diffusion. And something I also didn't really talk about, I just skimmed over it, is that you have surface fluxes, you have surface diffusion. Yeah, so if you have higher pressures or lower temperatures, you may have a significant flux alongside the surface. This needs to be included. There's beautiful work on membranes by Andreas Seidel-Morgenstern and colleagues, who also demonstrate the importance of the surface transport, right? So it's clear there are all sorts of viscous components that may have to be included. And so a dusty gas model could include all of this, or the other models more sophisticated can include that. And so yeah, so all these factors could need to play a role. And if you have a multi-component situation, you will have fluxes that are not just fixed law, but more of the Stefan Maxwell type of extension of this, which is the dusty gas model.
Yeah. Okay.
Hope that answers the question. So that's clear.
Yeah, I think it does. Yeah, perfect. And we have a final high-level question. So we have these multiple simpler models, the approximations that you spoke about. How can we connect them to, let's say, a reactor model, for example? Wouldn't adding all of these models make it computationally expensive?
Well, so I'm trying to see which slide this was in again, but why don't I find it now? Well, I described earlier the impact, say, on a reaction with catalytic reforming of naphtha, right? Don't know why I don't find the slide now, but of this fractal surface roughness. Yeah, here it is, right? This was several reactors in series, and this work was done during my PhD in the 1990s. So if you can do it then, I think you can do it today. So there is really, what I want to say, there's no excuse. There is really no excuse. You can include those factors already easily. The fact is that saying that you have, it's just the same as, say, even the effect of pore length. This theory is not more complex than the original Knudsen diffuser. It's just wrong to use an infinitely long pore if it's short. Just use the correct formula. This is actually a challenge, and it is almost incomprehensible that this is decades ago. This shows you that some things just get perhaps discarded or just all lumped in one factor, and it seems like this could work, right? And so if you have a reactor model, this calculation, by the way, was done with Stefan Maxwell equations, multi-component, including Knudsen diffusion, molecular diffusion, interaction between species, and Langmuir-Hinshelwood kinetics, already in the 1990s. So this was my PhD work. So it can certainly be done today with microkinetics, even, and topological effects. And that's what I showed in the work by, my colleague, Guanghua Ye, where we did pore network models, and we included multiphase effects. And so here you see effects where, this is moving here, where it demonstrates, thanks to that, being able to have the experiments on a reactor, right? And compare it between discrete and continuum. It can demonstrate that in this case, if you have condensation and hysteresis effects, that you must include pore network effects. So this is a situation where it demonstrates this. If you don't have these condensation, single phase, you don't need that. You can use a simpler model, you see? So you see, so you basically get an insight of when do I need which level of complexity? What is the type of bull I need to use? The one that's very refined, or can I use one that has a few lines? Yeah.
True, yeah. This is really interesting.
But they need to be properly drawn, though, the lines. It was Picasso. Yes.
Perfect, yeah. I think those were the questions that we had. Thank you so much, Dr. Marc-Olivier.
Thank you so much for having me.
Thank you. I'll hand it over to Nicholas Wilkins.
Yep, I'll take the screen back now. And Marc-Olivier, if you wouldn't mind just turning off your video and audio for the time being.
Of course. Thank you again.
Thank you. All right, I'll share my screen. Thank you, Dr. Marc-Olivier Coppens, for your presentation, Diffusion in Mesoporous Materials, Linking Theory and Experiment, for our special IAS webinar series, Diffusion in Nanoporous Materials, Guidelines for Measurement and Reporting, focusing on the recent IUPAC technical report titled Diffusion in Nanoporous Materials with special consideration of the measurement of determining parameters. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. The edited version of this webinar will be posted on the IAS YouTube channel and Bilibili with an announcement on the IAS Twitter feed. The hope is that the work discussed will be a useful resource for the adsorption science community in the future. The next confirmed IAS webinar will be given 2 weeks from today by Dr. Enzo Mangano on April 9th at 1400 UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed, LinkedIn page, and through the IAS mailing list. With that, we thank you for joining and hope that you will join us again soon.